a few things in the chat. Alejandro's asking me to go over the quiz a little bit, and Kevin's asking if I can do some small content on file IO operations in Java. So Kevin, I actually did all the file IO for you for the assignment. You just have to write the method that actually already just takes an array and determines, or I guess, sorry, takes its parameters to arrays and determines if they're quote unquote match. And we came up with our own definition for what a match is for that particular problem. I can do some videos, but again, if we look at what's given to you, like, yeah, you're just doing this method here, which, again, it's given to arrays. You're returning true or false, whether or not they're a match. And again, in the PDF, I kind of talk about what a match actually is. But what you do is when you're going to run the program, you're going to say Java mystery array, the program name, and then just give it one of an input file. And I've given you some sample input files, but you can also kind of come up with your own. And then what it does is this A3 setup actually creates a scanner that's going to scan through the file and kind of read stuff from that file to set up those arrays appropriately. And then it calls that match function and determines whether or not your match method returned true or false. So yeah, the main thing you're going to have to do is just this match method that again determines whether the two arrays you pass to it are matching or not. And I mean, I made a couple helper functions within this. So within this match method, I called some helper methods, but yeah, you don't actually have to do any of the file IO. But I can kind of do some videos this weekend possibly. So what else? So the quiz, actually, yeah, we'll go over the quiz in a second because I do have some midterm stuff to talk about. So for the midterm, again, I finished grading it last evening. It wasn't too late, but yeah, certainly I haven't had as much time as I'd like to kind of go through and determine exactly what I'm going to do about it. I've also emailed a couple other professors in the department about kind of what my options are going forward. Again, for me at this point, the average is low enough that I certainly want to do something, but I just want to make sure what I do is just kind of fair for everyone. Again, my I guess stance on kind of exams and I guess grades overall in a course, or that I feel like I hope the people's grades reflects how well they understand the content. And I think certainly the scores in this midterm don't reflect how well most of you do know the content that we've covered over the first month. So if we scroll down a little bit, this is what the curve looks like. It's out of 45, and as you can see, like there's very few people in the 90s and 100s. There was actually someone who aced it, but again, I think like out of 106 people, there was only like 13 or 15 above 80%. So quite a small number of people. And again, because the last question was worth 11 and you weren't able to do anything on it, that's already taken you down to like, without any mistakes, right into the 30s, right? So, so I know in lecture on Wednesday, some people said like maybe drop your worst question. I'm not sure if just a raw scaling is the best thing. So I guess then the curve would look something like this if I scaled it down a bit, where again, if it's just only out of 30 something, then again, a lot of these, the curve's a little bit higher. But again, I'm going to kind of see what the best options are, or again, some sort of thing where if you're able to do better in later midterms, that can kind of override some of the stuff from here. So Yeah, it's something I've sent some emails, but I haven't actually been able to meet with any of the other instructors, but I'm hoping to kind of get some of that done this afternoon. I will release the grades after class, or I will release the feedback after class and the solution, so you can actually see what you did right and wrong. But again, just at this point, all you really need to know is that there is going to be something that helps helps hopefully those of you receive a grade at the end of this course more aligned to what you hopefully have learned. Any questions about this so far? So again, the average was, or sorry, the midterm was out of 45, and the median were in the 25. So again, not great. Yeah, so like high 50s, whereas like I'm used to exams kind of being at least 15% higher than that for the mean, and kind of even 20 or 25% higher for the median. So yeah, we'll certainly do something about this. But I again, as I said, when I talked to some other instructors, previous instructors from this course earlier this week, a lot of them said that they had averages right around 50% for the first midterm. So it's clearly something that has happened in this course before, and I assume that there's a few different things that these people have tried to I guess shift that weight or alter those grades, and so I just want to check in with them to see what worked and what didn't when this happened in the past, and any suggestions they might have. Any questions about any of this?
Hey, Anthony, so will you be releasing the raw grades as well, or just the answer key?
Yeah, I'll release. I think I can make it so you can actually see your submission and your feedback. And I guess, yeah, so what I'll do is I can download this. If it works, I can download this by question. So like, again, if I was just to drop everyone's lowest question or part score, I could do that quite quickly in Excel. So again, there is the way that I can download this is it goes, again, these had set kind of different values there. But I can kind of, what I'll probably do this weekend is take a little bit of a deeper look into how, I think maybe it was Andy or something like that suggested just dropping the lowest part score, how that affects people versus just like a raw kind of grade scaling versus I guess some other things associated with shifting some of the weight of this exam or something like that into midterm 2. So yeah, probably there's still a lot of things on the table at this point, but yeah, you'll be able to see exactly what you put and what feedback you got. But at this point, I just wanted to make sure that when you see that score, that you realize that there is some things in the works to being done, and I'll hopefully be able to talk about that on Tuesday. Yeah. So for sure, Ty. Any other questions? Okay, so someone also wanted to go through the quiz. Oh yeah, it's all organized differently. Okay, submissions, pretty good. So I guess the main thing here is that it was supposed to kind of be testing this slide here where we've got these, where we're determining how to, I guess, create the subarrays that we'll check because during the next iteration. So what we've got here is, actually I might need my keyboard still a little bit. is in the way that this algorithm works. Again, we've got these kind of two integers, L and R, which are just actually keeping track of the index value. And again, this isn't necessarily index 0, 1, 2, 3, all the way up to 4, 5, 6. This could be somewhere deeper in the array, because this could already be the subarray based on a previous partition. But at any given, I guess, kind of version of this recursive algorithm, you're gonna have this space where there's a range of values within our original array that this particular subarray is part of. And our idea is that we'll set P to the right element, and then we'll use these other array or integer variables to keep track of really just making sure that when I put this pivot into its right location, all the values to the left of the pivot have a value or a key or whatever it is less than P, and all the values to the right of the pivot have a value that is greater than P. Or, sorry, have a value that's greater than, so that are, all these values are greater than P. And how this algorithm does is it says, okay, well, this L is going to keep track of all the things to the left of the, or to the L and left should be less than P. And all the things to the right and to R and to the right should be greater than P. So it kind of just, they scan through. Again, we're going to start with the leftmost index and scan until we find a value greater than P for our L. So how that's going to work is, again, it's going to scan and says, okay, yeah, 58 is greater than 21. Then the R is going to scan to the left until it finds a value that's less than the pivot, so that's 5. And then again, because we want all of the ones that are smaller on this side and all the ones that are bigger on this side, we're just going to swap those values. Oh, sorry. And I don't know why. I didn't even know I could do that. Cool. Okay. And then again, the L is going to keep scanning to the left and until it finds another one, and the R is going to keep scanning to the right until it finds one, and then there's going to be swapped. And then again, as long as L is no longer less than the right, we know that, okay, I've got all the high values on one side and all the low values on one side, and now these two have crossed. So again, when they've kind of crossed here, we know, again, everything over here is less than the pivot, everything over here is greater than the pivot. So then we just know this is the spot where the pivot should be. So at that point is when we can kind of swap the pivot into that spot. And now we've got those, and now this will be the next kind of subarray. This will be like array A2, and this will be array A1 for the next kind of version of the recursion. And then again, within A2, we'll say, okay, this is the pivot, and this is going to be L, and this is going to be R, and they'll do the same thing. And saying this is going to be the pivot, this is going to be L, this is going to be R, and they'll do the same thing. And so this is the process that keeps recurring slower and slower, and then we'll have kind of subarrays from there as well on either side of the pivot. And that's the idea that is supposed to happen. So on the quiz, or for the quiz, when we're saying which element could have been the pivot, and we've got this sequence here. Oh, it's on 2 lines for me. Gross. And we've got these values 11, 4, 20, 45. No, they don't always increment the same rate. They're going to keep finding values they're only doing it based on the pivot. So I guess the idea here is we could say, okay, if this is the pivot, after I've finished this process, I've moved my L's and R's, then everything over here has to be less, and everything over here has to be right. but we see there is a number to the right that isn't less than 11. So this can't be the pivot, because at every iteration, the pivot actually gets placed into its correct location with the right number of elements on either side of it. So again, we know that 11 can't be the pivot. What about 4? Could 4 be the pivot? What do you think? Why not? Yeah, so again, this is great. This checks out. All these values are bigger, but all these values are not less than. That breaks it. And again, that's kind of what I was expecting you to go through, is really quickly say, okay, could any of these values, could this be the pivot? Are these all less? Yes. Are these all greater? Yes. So 20 looks good to me. 45 could this be the pivot? Are these all less? Yes. Are these all greater? No, this one breaks it. So it can't be 45. Similarly, this will break the 32. 70. This looks good. This breaks. Yeah. And I guess this will also break the 98, and the 98 and 70 will break the 60. So it looks like for this one, it was only 20. But does that process make sense of how I can kind of see what the pivot must have been in this case? Yeah, so again, this wasn't a great pivot, but yeah. It just means that now the next subarray, array A1 subarray will be this range, and A2 will be all of these. And then again, it'll start with the pivot here and try to think about making sure all, I guess at the next subarray A2, it'll end up kind of, my L will I guess go to here, and my R will go to here, and then it'll kind of swap the 60 and the 70. So we'll have, and this will be the next pivot because it's in the right place, and then these will be the next two subarrays. So I think on the next question there were a few more, but again, it was just that same process where you want to say, okay, is everything to the right of this 15? I guess I'll just actually just write a 15 down there. So again, we got these values. Is everything to the right of the 15 greater? There's something to the left. So again, all these are greater, so 15 works. 22 is everything greater. No, the 17 isn't. 17 is everything less than on the left. No. 31 is everything less than over here. Yes, it is. Everything greater over here. Yes, it is. So the 31 works. And that's kind of just the idea here. I kind of wanted people to go through. Any other questions about this? Why isn't 11 the pivot in question 1? So again, our values are 11, 4. Because 4 comes, we couldn't say that these are all the values greater than 11 because 4 comes after 11. Yeah, okay, cool. Any other questions? Okay, so I mean, you might have noticed I didn't post a new worksheet today. It's just because we are a little bit behind. I think what I probably would have done if we got to a little bit more on previous days is probably had this algorithm as a worksheet and got us to just trace through this pseudocode one line at a time and seeing how our L's and whatnot were updated. But instead, I kind of put this over to a video. And what I might do is split up the video kind of into the first half of what you saw, because I know it was a long video. And kind of have the video that overviews kind of how the quicksort algorithm works, and then maybe have another set of videos, one about this partitioning algorithm, and there's some other ways that you can partition and choose your pivot and swap elements on either side of the pivot, which is really the key thing for quicksort that makes it work well, is you want people to choose a pivot really quickly and hopefully a good pivot, and then just make sure that you have elements on either, you put the elements on either side of that pivot, and recurse on those subarrays. In this case, the green and the red subarray. So I might kind of break that video up, do one on just this particular slide really, and then another one on another similar slide that partitions in a slightly different way. But I'll see if I can do that over the weekend. It takes me a while to make these, and I'd like to make another one with a different partitioning algorithm, but just the slide just takes a lot of time when my PowerPoint starts going super slow when there's just like so many animations that are kind of after one another. And so some of these just had just animations on animations on animations to get them to work and getting that timing and stuff going. Yeah, you can ask a question about assignment 2, and then we'll maybe jump into the merge sort worksheet. Oh, sorry for the current assignment. Yeah. So do you have to write pseudocode for push and pop? No. Again, what I'm expecting you, if you've got 2 queues here, to just kind of say, okay, we're gonna like use NQ and DQ from Q1 and Q2. Like our push operation will just be doing some NQs and DQs or whatever you think how it's gonna work, and then the pop will be implemented by, again, doing some NQs or DQs from these 2 queues. It's just more of a higher level description. You don't have to actually write any pseudocode here. You will be writing some pseudocode right here to figure out a recursive way to I guess reverse a linked list. And then I talked about this a little bit at the start of class, but then this one you'll just be implementing the match method. I've done all the IO for you, and I've given you some sample files. And again, but I do think this kind of takes a while more to just visualize how it works. Yeah, you're using queues to implement the stack. Yeah, you really just want to use queues. You're trying to do using queues to get this last in, first out behavior. Yeah. Any other questions? Where's our schedule? Okay, so I think we should have enough time to get through this merge sort. Okay, I'm gonna grab my tablet and probably do mostly tablet stuff from now on. Okay, so the first thing we typically do on these is think about the running time. And this one is a little bit more difficult because we have some recursive calls here. So I guess what we're going to come up with is a recurrence equation first. So I guess, first of all, we've got this base case here, which again, if we're counting the number of comparisons, it's really just going to be probably one comparison here. But yeah, typically, again, no matter how we implement this, the size method that we're calling isn't going to have a large runtime. But we can say, again, we can count this as 1, or depending on how many operations we're counting, again, if we're counting assignments and stuff like that, this is just going to be, why don't we just label this as B? So this is going to be the base case, and it's going to be some very low constant number. Then we know we've got this divide method here that all it does is it says put the first half of the elements into one subarray, put the second half of the elements into another subarray. Again, this is merge sort. We're backtracking to merge sort before quicksort. Where I guess I can scroll down and show you. Again, the merge sort, all it does is it breaks an array into two that are half as big, then breaks those two into ones that are a quarter as big, then an eighth and 16th up until we have one element, and then it merges those two trivially sorted arrays. So again, we're going to say the base case is just B. We know that this is going to take, I don't know, it's going to take, again, some very small constant times n, because really you're just going through and you're saying, you've got a for loop that's just going through all the array. And similar to the merge, we've seen that we can do that in some very small constant n. Where we're just saying, now we've got these two sorted arrays, we have those 2 pointers at the beginning and saying, which one's smaller? Let's copy that one into that merged array. But these two are where things get a little bit more interesting. And again, really what these both are is they're, again, the function, merge sort function with an input size of n over 2. They're saying solve the problem, but with this merge sort again. Again, it's just calling merge sort again, but the array it's giving it is going to be half as big as the original problem. So what this is going to look like if we were to write a recurrence equation is going to be that we've got our T of n, and it's just going to be B, which is, again, probably going to be some very small number. It's going to be B when n equals 1, and it's going to be, we've got 2 of these. Plus some constant number of, so some like probably basically like plus 2n or some very small number times n. Does that make sense? And so this is the first time we've really looked at a recurrence equation without, I think, without actual like numbers here. We've got some C's and some B's. So we're still going to try and solve this by substitution. So again, what we've got and how I typically do this is we've got Tn equals 2t of n over 2 plus c of n, which we can also say that if I want to know what t of 10 over 2 is, it's going to be 2t of n over 4 plus c of n over 2. T of n over 4 is going to be 2t of n over 8 plus c of n over 4. So again, all I am is I'm replacing the n with n over 2 or n over 4 or whatever other things, just to visualize what doing that substitution is going to look like in my later steps. Since I've got this all in red, what I'm going to do is write this in purple, just so it doesn't overlap with the substitutions that we're doing. So again, we've said this is B, this is C1 of n, this is C2 of n, and this is 2 times both of these are T of n over 2. So again, so now let's actually start trying to solve this by substitution. We again know that our T of n is 2t n over 2 plus c of n. And now I'm just going to replace this with, and I'm just going to do a replacement here. I'm going to replace this t of 2 over n with everything I have on this line, right? Because I'm saying I know what t of 2 t of n over 2 is right here. It's 2t of n over 4 plus c of n over 2. So I'm just going to make that substitution. So 2 times 2 t of n over 4 plus c of n over 2. Let me erase that, clear that up a bit. Plus the cn we had before. Which, and if I kind of do this multiplication here, I've got 4t of n over 4. If I multiply this 2 here and also this 2 here, that's going to cancel out. So this is just going to be cn plus cn, which is going to be 2cn. So again, all I did here is I multiplied out, I multiplied the 2 times this 2 and the 2 times to this term. And so these 2's canceled out. Whereas the 2 times 2 made it 4. So now again, I can do another substitution right here, because I also know what that is. So I'm just going to make that substitution. Oh, sorry, I don't know why I put a 2 there. It should be a 4 now. Where am I going? There I am. 4 times 2t of n over 8 plus c of n over 4 plus the 2cn remaining. And again, if I do this multiplication, we're going to see we've got 8t n over 8 plus 3cn. How we eliminate C? We'll get there eventually. We're actually not really going to, but we'll get there in a second. So I think what we might be able to see at this point is T of n equals, and maybe you want to do this one more step until you kind of see this pattern. But what I'm seeing is it looks like my Cn value was 1, then 2, then 3. Whereas my coefficient I'm multiplying to the t term is 2, then 4, then 8. And again, this is 2, then 4, then 8. So I can kind of start seeing a pattern here where the C coefficients are just going up by 1, whereas the other ones are multiplying by 2. C is just saying that to do these merge and divide steps, it's going to take O of n time, but it's going to be times some small constant. So slightly, it's not just n. It's going to be like 2n or 2n plus something really small. Yeah. So this point, what I'm seeing is that if I want to think of how these terms are relating to each other, I think this is actually 8 is and maybe I can actually write this. I could actually say that this is 2 to the 3 t of n over 2 to the 3 plus 3 cn. And this one here would have actually been 2 to the 2 t of n over 2 to the 2 plus 2 cn. Oh, not m. And this is 2 to the power of 1 times t of n over 2 to the power of 1 plus 1 cn. So what I'm noticing with this pattern is that I've got 2 to the power of some I times t of n over 2 to the power of that I plus I times cn. So I've got a lot of a lot of different variables there, not actual many numerical values, but at least we've got a pattern going here. So what I want to do is, as usual, we want this term, we want to go to a t of n that is a term we know, which we know how to evaluate it when t is equal to 1. We know it's going to be that base case, which is really just some number of operations, a really small number, like 1 or 2 or something like that. It's just a single comparison there, and I guess a single assignment. So we want this to get to t of 1. And so what we're going to do there is what we want to be able to do here, we want n over 2 to the I to equal 1. So what we can do is we can multiply 2i to both sides, and we'll have n equals 2 to the I. And then to solve for I, we can say log base 2 of I, which is how we're always going to write our law, equals n. Or sorry, I screwed that up. Sorry, log base 2 of n equals I. Yeah. So now what we can do is we can actually plug this in over here. What we've got is 2 to the I we know as n from here, times t of n over 2 to the I, which is going to be 1, plus I, which is log n, or log n, I guess, times Cn, which is going to be n times the base case, which is b. This is going to be 1. So this is b bn plus Cn log n. And at this point, we know that again, this b is a really small number from up here. And we know that so again, that leaves us with this Cn log n. But if we think about our big O notation, the definition of big O is that we're trying to find a constant C for which it fits under some curve. So we've actually just got a constant there, C there already. So we know again that if we were to do, I guess, like a big O from here, we know that this could always be less than or equal to bn log n plus Cn log n, which is just going to be, which we'll see this is eventually just classified as n log n. So what we'll say is that this is O of n log n. Kind of out of space there, but yeah, so I had so this I went to the log n, and then I kept the Cn there as well. So instead of actually counting them up one by one here, at this point, we know that, again, I called B the base case, which is if we were to count up all the number of operations that happen right here. So again, it depends if we're counting comparisons and assignment statements, it's going to be 2. If it's just comparisons, it's going to be 1. But no matter what, this B is going to be a really small number. In terms of the C's, again, when we're dividing an array, that's going to be, again, it's going to be a for loop that just goes through n and says, essentially, if n is in the first half of those numbers, put into array 1. If it's in the second half of those numbers, put it into array 2. So again, it's just going to be basically n times some small number of additional operations. And that's similar to the merge, which we saw in the videos where, again, we've just got these two subarrays. They're each size n over 2, but we're going to go through all n over 2 of those elements and copy them down to the other array. So again, it's going to be more or less just both of these are more or less just going to be a loop that goes through n times. Does that make sense, Leo? So I guess like it depends on if we're counting just comparisons or if we're counting comparisons and assignments, like then like if we're just counting kind of comparisons, this B would probably just be a 1 because it's just a single comparison. And these would pretty much just be like this would be like n plus 1 because again, it's just a for loop that's going to have the n comparisons that are true that go into the loop and the 1 after. So again, but really this is just really close to n, and this is really close to just some constant value that isn't going to be have a big impact on our overall running time. Like we know this isn't going to be like n squared or anything like that. It's going to be within the realm of n plus maybe a few extra operations to set up the for loop and whatnot. Kind of makes sense? So that's why we're at this point just kind of, now that we've done this kind of asymptotic analysis, we are just kind of mostly focusing on the n terms and knowing that this is just going to be some small coefficient that isn't going to have a big deal, and this is again just going to be some coefficient we multiply by n. But again, if we think about how we do our big O classification, we're saying, is it under this curve with multiplied by some constant? So that's just going to be the constant that we'll say is our C when we do our big O. So again, down here, this is pretty much with C equal to C and n not equal to 1. So again, we just got that. So we don't actually know what it is, but it's going to be something small. Any other questions? We got 7 minutes. Okay, so I think I might actually have to clear this if I go down. Oh, I guess not. Kind of still fits, but so one interesting thing here is that merge sort and selection sort, but merge sort, all of these are the exact same asymptotically, because again, it doesn't actually matter if they're all sorted or not. It's still gonna keep splitting them up until they're just a single element, and then put them all back together. So even if it was already perfectly sorted, it would still split them all down into size n over 2, n over 4, n over 8 until they're just a single element, and then merge them back together. And it would do that if they're all reverse order, totally scrambled, already sorted. It's all of these like are going to be work the exact same. So I mean, in some ways, this is a good thing because it's consistent, and you know that again, you don't have to worry about the order of elements in our input data. Whereas, like for insertion sort and bubble sort, we might get drastically different runtimes depending on the contents of our input array. What do we think for stability, though? I think it's better kind of, unfortunately, it is better doing this example before doing quicksort. Because I already alluded to the fact in the quicksort video that for some of these things, some of the issues. But I guess, so for stability, the main thing that we need to think about for stability is when we're actually merging them back together. So again, what we want is essentially yes, and how we can make sure it's stable is when equal, or what am I actually? So up here in the merge, when we've got kind of two arrays, and we've got two arrays that are both sorted, and we're trying to merge them into a bigger array, what we're going to do is we're going to, again, have these different pointers to keep track of where we are. And we're going to say, which one's smaller? Okay, the one's smaller. Let's grab the one and put it here. Then this pointer is going to go one forward. Then which one's smallest? Oh, the 3 is smallest. Okay, I'm going to grab the 3 and put it here and then move that again one forward. And which one's smallest? Oh, the 4 is smaller. So I'm going to now grab the 4 and move this one forward. So again, we've got these two sorted subarrays, and we're just merging them into the larger array. But now that I've got a tie here, they're both 6s. Is there a way that we can make sure that this is stable? That's the question. We want to make sure we take from this array. Yeah, because we know that the left, all the things on the left are, if something came before it in the original array, it'll be on the left side of it. How can we do that in the code? What line of this code here is important to ensure that? Yeah, so here we're saying if the array at I of 1 is less than the array of j, then grab it from I. But yeah, if we had this less than or equal to, then it actually is stable. Because we're saying if there's a tie here, then grab it from array A1. So in that case, I'd say, okay, there's a tie. Let's grab it from A1. Let's grab the 6 and move this one forward. So I'll say, yes, it's easily made stable by ensuring left array elements are chosen during the merge. I guess during a tie. Does that make sense? What about for memory usage? Yeah, so we need it's O of n, because we need an O of n sized an O of n sized array is used to temporarily hold the elements. Yeah. So again, as our input size is bigger, we need to actually use more and more memory to actually hold those temporary elements. Because again, what's happening is we've got, like, I guess we can use this just using, we can kind of break this up just using indexes in the original array, but then we create another temporary array when we actually merge them together. There are, what I will say is there are variants variants that are better. Whenever you're doing the merge, David, you've got elements in the original array, and you're essentially creating another array that's the same size as those two combined, and copying them from this one down into that temporary array. Does that make sense? Each merge, but you can, if you think about it, you can actually get away with only allocating an array of size n in total with all the merges combined. Because even when if you're merging, you're going to merge kind of like 2n/4s together, and that's going to make an array of size n/2. But when you merge the size n/2s together, that's going to be merged into an array of size n. So there's going to be maybe smaller little arrays you're allocating, but again, it's always going to be, you can kind of clear out this space before allocating a new array of size n, but always all the n/2 is going to add to n, all the n/4 is going to add to n, all the n/8 are going to add to n. There's always just going to be the total amount of additional space you need to allocate to do that merge is never going to be bigger than n elements. Does that make sense? And the nice thing about if we did this with a linked list, instead of actually having to allocate another nodes or array anything to do that merging, you're just, again, when you're merging, you've got all these different elements, and you're just kind of updating their pointers accordingly. So instead of it being one's next is 3's next is 6, next is 7, you're just saying, oh, 1's next is 3, 3's next is going to be 4, 4's next is going to be the 6, 6 next is going to be the other 6, and you can do the merge. Obviously, there's a lot of wrangling of kind of updating the next pointers and stuff, but you don't actually have to allocate any more space. What I'll do a recap of this on Tuesday before we get into our next unit. But the big issue with merge sort compared to quicksort, which is another n log n algorithm, is associated with this memory stuff. So I have a few extra slides that I don't think I talked about in that video. I forget, actually, I did so many takes, so I forget which one I actually posted. But we're going to talk about why, again, although these running times are very good, and basically as good as you can get when we've got this log n, why something like quicksort, which isn't always even necessarily n log n, is typically chosen over merge sort, is because of some of the latency associated with this extra memory usage. So memory operations can actually be quite expensive. So what we end up seeing is that even though quicksort isn't necessarily always going to be perfectly split like this, in reality, even if the partitions are just okay, it typically still has a better running time than merge sort because of all of this extra memory overhead. But that's something we can look into a little bit more on Tuesday. Maybe we'll just spend a couple minutes doing that, and then we'll jump into our next unit. Any last questions about this? Okay, I'll stop recording. I'll stick around. I do have office hours now.
The recording has stopped.
For the next 2 hours. So